the planets aren't perfect. Aren't unlike any planets in our own solar system. They're completely different. We're discovering quite a diversity of worlds, and there's many people, including people here at UCLA, to try to explain, how that diversity of worlds comes to be and why we have all these different kinds of exoplanets. One other thing you'll notice is that if you look at the color coding, there's thousands of planets, but you can literally count how many planets have been directly imaged. Those blue circles, there's not so many directly imaged planets. Okay, got it. This is because direct imaging is hard. To directly image a planet, it's kind of analogous to trying to watch a firefly circle a street light if you're standing several miles away. That gives you the context for the brightness ratio, the flux ratio between the planet and its host star. I got some echo. Okay. And it gives you some sense for the angular separation, how closely separated in the sky the firefly is from the searchlight. We're talking about 0.1 to 1 arc seconds. This is a very, very small angular separation. But we can do it. So here's a cartoon graphic I drew for how to image an exoplanet. We right now have the technology to really image Jupiter-like planets next to their bright host stars. We're generally doing this from the ground, so things like atmospheric turbulence gets in the way and blurs our images. So what we have to do is to correct the atmospheric turbulence using a system like adaptive optics. We also want to block out the bright glare of the star, so we have something like a coronagraph to remove the glare of the star so that we can actually take a picture of that planet. So how does this work? So here is an image of a star without adaptive optics. That's that fuzzy blob you're seeing there. This is like multiple exposures taken over the course of several seconds. You can see this fuzzy blob move around. This is the Earth's atmosphere blurring the image. And if we turn on adaptive optics to correct for the turbulence in the atmosphere, basically constantly providing corrections to counteract the turbulence in the Earth's atmosphere, this is the image that we see on the right. So that fuzzy giant blob becomes this crisp point source in our images. And if you look very carefully, in addition to that point source, there's actually a second point source in the image. This is actually a binary star. It's about 100 times fainter than the primary. And if you're looking at the image on the left, you would have completely had no idea that binary star was there. Exoplanets are about 1,000 to 10,000 times fainter than that binary star. So you can imagine why this is why adaptive optics is absolutely needed for us to image exoplanets to correct for the glare, to correct for the blurring of the image to the Earth's atmosphere. But this alone is not enough. The glare of the star, just the fundamental wave-like nature of light and the fact that it diffracts makes it also equally impossible to image an exoplanet. So this is an optical simulation assuming zero atmospheric turbulence. There's perfect wavefronts imaged with an 8-meter telescope. And it's a simulation with both a planet and a star in the image. But you can't see the planet at all. It's hiding underneath the diffraction rings created by the host star. So even with perfect adaptive optics, even if you're able to have no adaptive optics, say a space-based telescope, because of the fundamental wave-like nature of light and the fact that it diffracts with itself and interferes with itself, creates these ripples that basically hides any faint exoplanets we're trying to image. So this is where a coronagraph comes into play. A coronagraph suppresses the diffraction and enables us to see faint planets that would have otherwise been hiding underneath the glare of the star. So this combination of both adaptive optics and some sort of starlight suppression like a coronagraph is used for us to see these very faint exoplanets up right and close to the bright star that they orbit. So here's some real images of exoplanets. On the left, so the animations are kind of spectral cubes, so they're going through different wavelength slices. You're seeing images at a bunch of different wavelengths in the near infrared. On the left is one of the brightest exoplanets that's ever been directly imaged. On the right is one of the faintest exoplanets that we've ever directly imaged. So I challenge you to try to find the exoplanet. Give you a few seconds. Some of you guys aren't allowed to guess because you have seen this data before because it's from the Gemini Planet Imager, which folks at here at UCLA helped build. So how about on the left? You guys, where is the planet? Here?
Yeah.
All right, you think it's there? Anyone, any other guesses? 2 o'clock. Here? Here? This thing? This thing? This one? Okay, how about here? Where's the planet? Top left.
No, closer.
There? There? All right, so indeed, beta Pig B is right here. That is one of the brightest planets. This is after adaptive optics, one of the best adaptive optics systems we've ever built, after a chronograph, and this is the brightest planet we've ever directly imaged. And then here, this is a trick question. You can't see it. So it turns out, even with our best instrumentation, we still also have to do data processing to see these directly imaged planets. We use specific observing techniques to disentangle the residual glare of the star from any astrophysical sources. I have to turn off my sound. Some of these techniques is called, basically what we do is we take data, we use data taken at other times and other wavelengths to model and subtract off the glare of the star. So how this can work is with this thing called angular differential imaging, we can basically take advantage of the fact that the Earth rotates and therefore the sky from our point of view is rotating. So any real astrophysical sources like a planet rotates over the course of the night as the sky rotates, whereas the diffraction pattern, which is set by the telescope, doesn't rotate and remain static. Similarly, on the right, we can use the fact that the diffraction pattern scales radially outwards as a function of wavelengths, whereas the planet stays at the central same location to, again, disentangle the light of a planet from the diffracted glare of the star. And how we use this information typically is we use these data-driven methods. We have acronyms for them. One of them we call is CLIP. And the whole idea is that we use images of the glare of the star taken at other times or at other wavelengths or of other stars to build an empirical model of the glare of the star to subtract it off. So you can see that here on the top left, this is a frame of data. So you can see mostly what you're seeing is the diffracted glare of the star. On the top right, this is our principal component reconstruction of the glare of the star. And you can see that this is using images taken at other times and other wavelengths. And you can see that the two look pretty similar. We look pretty good. At the bottom left, this is a data minus model. And you can see that it's an animation. As we increase the number of principal components, the number of components we're using to describe the variations in the glare of the star, we can remove more and more of the glare. And we stack 55 of these residuals together over time as we add more and more principal components that relate to describing more and more of the variance of the glare of the star. We can actually see faint point sources appear in our data. So this is how we are able to see faint exoplanets buried in the residual glare of the star, even after adaptive optics and chronography. And this technique is what we conventionally use in the field right now. The limitations of this technique is limited by the optical stability of the system. The fact that images of the glare of the star taken at other times, at other wavelengths, or of other stars are not exactly the same. They're slightly different than the glare of the star that we're trying to subtract off in the image we care about. And that difference sets our kind of performance limit in kind of standard exoplanet imaging right now. This still gets us quite far. Even most recently, we just had this new paper put on arXiv. We're actually using these conventional techniques. Natalie Jones, who's a PhD student at Northwestern, found a new exoplanet. This is actually one of the few directly imaged systems of a planet orbiting a binary. So this is a 6 Jupiter mass planet orbiting at about 60 AU. You can see it right here. And it's actually orbiting a binary star. It's a 1.3 to 1.5 solar mass binary. Those are the two components. They're orbiting at about 0.2 AU on an 18-day orbital period. And of the directly here, you can see this is a plot of all the directly imaged exoplanets. And the star and the triangles, these are all the companions orbiting binaries. And this is the lowest mass and closest in system where we actually have a low mass planet orbiting a binary in particular at solar system scales, at scales less than 100 AU, the typical size of circumstellar disks that are used to form these planets. So we're still using these techniques, we're still finding new planets. And even in old data, this is actually data taken in 2016. We somehow missed the planet the first time we passed through the data, but through archival reanalysis, we were able to find the data, find these planets. However, we want to do better than what we're doing right now. So one of the things I want to talk to you about today is reaching kind of fundamental limits of exoplanet imaging with new physics-based computational imaging. This is a new project I've been undergoing with, it's a very fun interdisciplinary project. We're, as a group of us astronomers, also collaborating with people in computational imaging. Computational imaging is a field of using basically computational tools to produce the image rather than a camera itself to produce the image. And what we're concerned with is the fact that when you image an exoplanet, most of the times you see these nice, pretty pictures of directly imaged exoplanets. But what I usually look at is I change the color scale and I look at all this noise, which we call speckles. And what I want to do is how can we model out and remove all these speckles? These speckles are the fact that when we do that PSF subtraction to remove the glare of the star, those images at other times and wavelengths aren't exactly a perfect representation of the image that we particularly care about to see the exoplanet. And how can we do better? So this is a project led by a Northwestern PhD student, Rodrigo Ferrer-Chavez. And the whole idea comes from the fact that we do understand optics. If you have a star and an exoplanet and you propagate its light through an optical system with known aberrations, all of these physics is known. We can predict, we can calculate exactly what the output image should look like. And in fact, we have very good optical models. So especially for the James Webb Space Telescope, or JWST, very high fidelity optical models have already been developed as part of building this very expensive space telescope. We know exactly all the different masks that are used and how they propagate through the system. We even know what internal instrument aberrations exist that have been measured pre-flight before they launch the instrument. So we have these very detailed models of the system. So if you input a scene of the star and the planet, we should be able to predict exactly what that output image looks like. But telescopes aren't ideal. There's aberrations in telescopes. With the James Webb Space Telescope, it's comprised of a bunch of hexagonal mirrors that build up the telescope primary. Those mirrors warp and deform and bend, and those create aberrations. But the people that built JWST anticipated that. They knew that was going to happen. So JWST actually every few days measures how much of the mirrors misaligned and bent and things like that. So what you're seeing here are basically maps of how distorted is that primary mirror made of all those primary hexagons, it looks like. And these are two maps taken on 3 days apart, August 11th, 2022 and August 14th, 2022. They look almost identical by eye. If you calculate what the images of a star should look like if that goes through these aberrations, you can also calculate that, and they look nearly identical by eye. But if you subtract these two and look at what the residual wavefront error is between these two telescope alignment images, you can see that there actually are small, subtle differences. And when you subtract off these two calculations for how the glare of the star should look, there again are small, subtle differences. And those small, subtle differences is right now what's setting the floor and the sensitivity for how well we can image exoplanets. But what if we just, instead of doing that, what if we just model if we knew exactly what the aberrations of the telescope were, we could just, with our understanding of optics, we can just predict what the glare of the star should look like and subtract it off and look for exoplanets. So that's what we can do. We've now rewritten this in a computational imaging problem. This is a problem for people that work in optimization to figure out. So if we have some input aberration phi hat, this is just like what we think roughly what we think the misalignment of the telescope primary mirror should look like. And we pass that input aberrations through our telescope model, which is now a black box called F of phi. It will produce an output rendered image of what the glare of the star should look like, y hat. We can now compare our output image y hat to our real image, our real data taken y, and subtract the two. And basically, if we had a good estimate of the glare of the star, we would see the planet. And this is just an optimization problem. We want to minimize the difference between y and y hat, which is a function of our input aberrations phi hat. So all we have to do is minimize y minus f of phi hat. And if we do that, we can find exoplanets. It sounds easy until you realize phi hat has about 10 to the 6 degrees of freedom. So sometimes in astronomy, we model things with like 20 degrees of freedom, 20 parameters, and we start being scared about not being able to find solutions. Here, we're talking about millions of degrees of freedom. Fortunately, people in optimization, especially in artificial intelligence, have actually been working on this a lot. Neural nets have billions of degrees of freedom, and they have to figure out efficient ways to optimize them. So, and we built what we did was we built an auto-differentiable optical model. And what this allows us to do is utilize tools that have been developed for AI optimization to basically apply those same tools to optimize our optical models of James Webb, of the JWST. Doing so, you can see that animation again. You can see we can basically optimize all those 10 to the 6 degrees of phi hat and remove all the glare of the star so that there only exists now. We've subtracted off the glare of the star, and there's only a planet that remains. And we are able to do this. We were able to basically model 10 to the 6 degrees of freedom in a few minutes on a single GPU. So it's a very tractable computational problem now. And here, we're no longer relying on the fact that we're using other images of the star taken at other times when we know there's some wavefront drift. We know the mirrors have misaligned slightly and produced a glare of the star that's slightly imperfect. We're using our understanding of physics to calculate exactly what the aberrations are at the time that we took the images to basically subtract off the glare of the star and see this faint exoplanet that was hiding in the data. We first took a look at this technique in simulated data, and we showed that our method significantly outperforms kind of the conventional state of the art. It's called PCA or CLIP. So here you can see we've simulated a planet in some simulated data. On the left is the CLIP, the conventional PSF subtraction data reduction technique to remove the glare of the star to see the planet. And you can see that we can't really tell where the planet is at all. On the right is our new method, and you can see that we can see this faint planet that was completely buried under the residual glare of the star otherwise. On the right, you'll see a few of these plots over the course of the talk. This is a plot of how faint of a planet could we see on the y-axis, like how much fainter it is relative to the host star. So 10 to the 6 is 10 to the 6 times fainter than its host star as a function of distance from the star. So in the green, this is the traditional sensitivity curve from our traditional methods. In the blue, this is the kind of the fundamental limit. This is how faint we can go just by the limits set by photon noise and detector noise. And then in orange is our curve. You can see that we're nearing the fundamental limit on simulated data with this new technique. So that's all cool, but this is all simulated data, right? What does it mean to work on real data? Real data is always more complicated, has a lot more quirks. So we've been working in the last year to get this working on real data. And now I can confidently say it works on real data as well. So here's some comparisons. And so on the left, this is an image of a star that we haven't yet detected any planets around. So there's no known planets around the star. On the left is the conventional technique. You can see all the residual glare of the star. that's left over after that technique. And then on the right is our technique. And you can see that we've basically removed all that residual glare of the star that's dominating before. And we've also tested it on real point sources. Real sources was real stars with real sources that orbit around them. On the left is the conventional technique that's been used in the past. On the right is our technique. And for the connoisseurs in the audience, you'll notice that we can now see the area rings of this planet that were previously kind of buried in the glare of the star, showing definitive improvement in signal to noise over what's been done in the past. So the advantage of this technique is limited by how well we understand the optics detector and fundamental noise rather than the optical stability of a telescope. And the optical stability of a telescope is hard to do. For JBST, we're talking about nanometers of drift will basically affect our ability to detect an exoplanet. And here, we're able to overcome that and no longer have to worry about the fact that the telescope mirrors might slightly drift by like 1 nanometer and cause us to lose an image of an exoplanet.
Jason, is it sensitive on how close the planet is to the star? I assume that there is a place where there's too much degeneracy you cannot see.
Yeah, it's a good question. So, just like with any imaging system, as you go under the resolution limit of your telescope, we will no longer be able to distinguish one source from two sources. So once that planet is basically at the imaging resolution limit of the telescope, we won't be able to tell the difference.
It's not sensitive to.
It's the imaging resolution and the fundamental noise. As you get closer and closer to the star, you collect more and more photons. And because you collect more and more photons, your photon noise also increases by the square root of the number of photons. So as you get closer and closer to the star, you also lose sensitivity because there's too many photons of the star and the Poisson counting statistics of photons. Yes?
So you're trying to minimize the residual, but the planet itself is a residual. So is there ever an issue where a planet is like
yes
method ever?
Can we overfit the planet? So there's two things. One is the fact that a planet is an asymmetric point source in your image, and from just phase errors alone in a single optical plane, you can't actually produce a single point source. So even though we have 10 to the 6 degrees of freedom, we actually cannot produce a single point source like this with those 10 to the 6 degrees of freedom. Second, we can use the conventional techniques in machine learning, because machine learning will always overfit if you give it enough time. So there's a number of well-established ways for how to avoid overfitting. So we're using the same techniques to avoid overfitting that everyone else uses in machine learning as well. Okay, any other questions on here? I'll be moving on to something else now. Good. So exoplanet imaging, not only are we improving kind of the new on data reduction techniques, there's also new hardware on the horizon that's very exciting. In particular, I'm excited for the Nancy Grace Roman Space Telescope. I always tell people it's coming sooner than you think. The launch window is fall of 2026 to spring of 2027. So potentially in a year from now, we'll have launched the Roman Space Telescope. The Roman Space Telescope is doing a lot of interesting wide field imaging science, but I'm not going to talk about any of that today. I'm going to talk about the O in the Roman, which that little drawing stands for the chronograph instrument. And the chronograph instrument is a technology demonstration instrument to move us towards having the right technology to build the Habitable Worlds Observatory and image other Earth-like planets around other sun-like stars. So I'll explain why we need this. So this is a bit of a technical plot, but you have to bear with me. So on the y-axis, this is planet to star flux ratio. So how much fainter is a planet relative to its host star? And on the x-axis is distance from the star in arc seconds. Right now, with kind of the state-of-the-art JWST ground-based observatories, we're basically detecting planets about 1 million times fainter than its host star, 10 to the minus 6 times fainter than its host star, at about half an arc second in separation from its host star. That's kind of the current state of the art where we are. To image an Earth-like planet around a sun-like star at 10 parsecs away, we have to reach a contrast ratio of 10 to the minus 10, 10 billion times fainter than its host star at an angular separation of 0.1 arcseconds. We're talking 5 orders of magnitude of sensitivity beyond what we can currently achieve. That sounds very hard and very daunting. So, and this is what Habitable Worlds Observatory wants to get to. So to kind of minimize technical risk and try to understand how to get there, we're building the Roman chronograph instrument. The Roman chronograph instrument is hoping to reach performance numbers about 10 to the minus 8 to 10 to the minus 9 times fainter than its host star. Hopefully basically putting us within striking range, about only a factor of 10 away in sensitivity rather than 10 to the 5 away in sensitivity to build an instrument like Habitable Worlds Observatory. And I'll just say that the performance of the telescope is limited by the telescope architecture, the fact that it was a telescope gifted to us by the National Reconnaissance Office, and exactly the optical design of that telescope limits our sensitivity to 10 to the minus 9. You can ask me about why that is later, but that's if we didn't have that telescope, we could actually get to 10 to the minus 10. Roman will demonstrate several key technologies for exo-Earth imaging. So even though we're not going to be sensitive to exo-Earths, we're going to demonstrate the technology that, if put on an optimized observatory, could give us that sensitivity. In particular, we're going to be doing ultra-precise wavefront sensing. And what we mean by ultra-precise is we want to be able to control the wavefront to 10 picometer precision, which is a tenth of a hydrogen atom. So talking extremely fine precision. Well, to do this, we'll be using these large format deformable mirrors, which have been used on the ground, but we're going to fly them in space and understand how they work in space. To also do this, we have designed new chronograph masks with these very fancy artistic designs to suppress the glare of the star, like you've seen before, in order to see these exoplanets. When we eventually image exo-Earths, these things are going to be so faint, and we're going to do spectroscopy of them, that we're going to be talking about collecting photons every minute from the planet. So every photon of the planet counts. So we'll be trying these ultra low noise electron multiplying CCDs that basically allows us to count every individual photon from a planet, so that when we do this for exo-Earths in the future, we can basically use, we're not throwing away any photons from the planet. Every photon is giving us signal. And then finally, we'll be doing data post-processing like you saw before with all the stuff we showed with the kind of the conventional, what we're doing right now with James Webb, doing that in a whole new regime and a whole new contrast level where we've never really done before in a real space mission. To kind of show you what the first two things mean, this ultra-precise wavefront sensing and deformable mirrors, the whole point of this is that it will allow us to do this thing called dark hole digging. So dark hole digging is, imagine the star is here, and this is kind of all glare of the star that you see. And what we're going to do is move those deformable mirrors in the telescope to cause the light of the star to destructively interfere itself right in this particular region, this dark annulus, and basically remove and cancel out all of the starlight in this annulus, so that we can see planets in this annulus. So this is the whole technique of Roman that we're hoping to apply to habitable worlds, is doing this thing called wavefront control to dig these dark holes, so that something that was originally about 10 to the minus, originally there was about 10 to the minus 4 times starlight in this dark hole, and dig it all the way down to 10 to the minus. So we're rejecting about a factor of 10 to the 4 in starlight, removing about 10,000 times the glare of the star in this annulus, so that we can search for planets here that are much fainter than any planet we've imaged before. If we're successful at this, has some exciting science potential. It will potentially, I'll say potentially because we're not sure of the performance, but potentially allow us to get the first images of exoplanets in reflected starlight. And it will potentially allow us to get the first visible light images of exozodiacal dust, the dust that exists kind of around Earth and in the solar system. There's also other science cases, and such as measuring the properties of Jupiter analogs, measuring the cloud properties of currently known self-luminous exoplanets, and measuring the properties of circumstellar dust as well. The instrument is progressing very nicely. So here on the left, this is an image of the instrument kind of fully assembled. You can see all the pieces of optics here. I want to point out a few things. The deformal mirrors that are doing that 10 picometer wavefront control are these gold boxes up here. The chronograph optics are here. And one of my favorite thing is the color filters. The Roman chronograph is a visible light instrument. So all of our filters are in the visible. So you can actually, there's actually a pink filter and a green filter and an orange filter. These aren't false color. These are just the images of the filters, which I think is pretty fun. Now, this whole thing has been packaged together, sent from JPL here in Southern California over to NASA Goddard. It's been assembled with the rest of the telescope, the instruments, the electronics bus, the whole spacecraft assembly. The whole spacecraft assembly is now currently in a vacuum chamber for vacuum tests. It seems to be going well, and we're on track for fall of 2026 launch still, I believe. We're quite busy. In the meantime, we have lots of things to do. We're trying to identify the optimal science targets to try to image things like the first reflected light planet. What is the best target with the best visibility for us to do it? We have a lot of precursor target vetting. You can ask me about this later, but binaries around massive stars is one of our huge kind of concerns that we aren't sure about. We are simulating observing sequences, developing the data reduction pipeline, and the Roman chronograph has been guaranteed a 2,200-hour program on Roman, so we're trying to plan out how to best allocate those 2,200 hours to both demonstrate the technology for habitable worlds and potentially also achieve some of these ambitious science goals of such as imaging reflected light planets. Okay. So that's exoplanet imaging, but I just want to come back to this plot. So we have thousands of known planets, and it is indeed true that if you count them all, direct imaging has only a small fraction of all those thousands of planets. But we can make this plot in a slightly different way. Let's look at all the planets with spectral characterization. And I use spectral loosely, as this means we've observed this planet directly in 2 different filters at least. And suddenly those thousands of planets, the large majority of them have all disappeared. Of the planets that can be characterized spectrally, there's only these close-in planets that can be characterized as unresolved spectroscopy or photometry, and these further out planets, these directly imaged planets that can be characterized with spatially resolved photometry or spectroscopy. So one of the things what we're trying to do with the directly imaged planets right now, with our ability to characterize them, is try to understand where is the boundary of planet formation. We think planets like our own Jupiter form through this process called core accretion, where first the planet accreted a solid rocky core, and once that core is massive enough, it was able to accrete gas and undergo runaway accretion to eventually form these giant planets from what's called a bottom-up process. You start from a very small thing, and then you slowly build your way up to this very large thing. We think that binary stars and possibly most brown dwarfs form through a different process, not through core accretion, but through gravitational instability, where you have a parcel of gas that's cold enough and dense enough that's able to gravitationally collapse on itself and form, say, a brown dwarf orbiting a star. So the question here is, are all planets formed through core accretion and brown dwarfs formed through gravitational instability, or where is the boundary between these processes? Or maybe the boundary is not very clear. But trying to identify, where does core accretion stop and where does gravitational instability begin? Where is that planet-star boundary? So to study this thing, we can detect planets. If we detect planets, we can count the number of planets we detect and use that to measure occurrence rates. And indeed, if we measure the occurrence rates of giant planets and brown dwarfs, we find that giant planets occur more frequently than brown dwarfs. And that's one sign of evidence that these two are different populations. But that doesn't tell us more that that evidence alone doesn't tell us everything. When we can characterize planets, we can watch them orbit. And by watching them orbit, we can measure their orbital parameters to see how different their orbits are. We can measure their compositions through their spectra to look at how compositionally different planets and brown dwarfs are. We can also measure their rotation rates to, again, look for differences in how brown dwarfs and planets spin. So for the first part, for the next part, I want to talk to you about doing high-resolution exoplanet spectroscopy with the Keck Planet Imager and Characterizer. This is a testbed instrument that's been on Keck for the last 6 or 7 years. It's enabled R of 30,000 spectroscopy in the near infrared. It's led out of Caltech by Dimitri Mawe, but we've had a lot of contributions from people here at UCLA to help build things, including helping us interface with the spectrograph NIRSPECT. The advantage of going to a high spectral resolution is that at very high spectral resolution, you're able to resolve the individual molecular absorption lines in an exoplanet's atmosphere. And this allows us to unlock several new observables. So here, if an exoplanet is moving towards us or away from us, the individual molecular absorption lines will be Doppler shifted, either red shifted or blue shifted, and we can use that to measure the radial velocity of the planet. Oftentimes, and we don't get spectra that look like this, the planets are so faint that for any individual wavelength bin, the signal's noise is maybe 1. So like there's just as much noise as there's signal. But what we can do is use this technique called cross correlation. So we take a template, say in teal, and we shift it to basically try to see where this template matches with the data in orange. Then basically, once we get the templates lines to align with the real data's line, the real lines in the data, you get a peak in the cross correlation function. And this template matching way allows us to not only detect, but also measure the properties of these exoplanets. In addition to measuring the radial velocity, we can measure the spin of the planet by looking for rotational broadening. If a planet is rotating, then one side of the disk is blue shifted, rotating towards us. The other side is red shifted, rotating away from us. And every line gets rotationally broadened, which essentially smooths out that line. And that also in the cross correlation function broadens the cross correlation function, allowing us to measure the rotational broadening due to the spin of the planet. We can also do some other things, which for the purposes of this talk, I'm just going to skip. So how we do this is it's not an easy feat. This took us a little while to figure out. But here is an image of a multi-planet system. So this is the star right here. And there are 4 planets in this image, including one underneath this fiber right here, but you can't see any of them because they're all much fainter than the glare of the star, as we have learned in the beginning. So what we have to do is blindly place our fiber at the location of the planet and hope we got it right, and integrate for a few hours and hope we collected enough photons of the planet and also photons of the star, but to hopefully distinguish the light of the planet from the light of the star. The advantage of KPIC is that we can take images of the star at other positions and help us build a model for what the glare of the star looks like. So what we end up doing is that when we observe the fiber when we get a spectrum of the planet, we also get a lot of leaked starlight into our spectrum. So in the black is our data, and what we can do is basically reconstruct that data as a combination of residual starlight in blue that's leaked into our fiber, and the planet light that we're also collecting as well. You can see that the planet light is generally much fainter than the residual starlight, but the one advantage at high spectral resolution that helps us is that you can see that the lines of the star are drastically different than the lines of the planet. So we're able to use that spectral information to disentangle how much of the contribution of the total spectrum in black comes from the planet versus coming from the star. With this, we've been able to do a few cool things. One, I just want to point out is we were able to make the first compositional measurement of a protoplanet. So this is the protoplanet PDS-70b for protoplanet connoisseurs. So this is a planet that's still forming. We know that it's still actively accreting. It lives within a circumstellar disk from which it was born. It has carved a gap in that disk as it has formed. It's a giant planet about a few Jupiter masses. And what we've done for the first time is basically be able to detect both carbon monoxide and water in the atmosphere of that planet and place a constraint on the carbon to oxygen ratio. So how much carbon is in the planet's atmosphere versus how much oxygen in the planet's atmosphere to be less than about 0.6. And that number by itself doesn't mean much if you don't have something to compare to. What's also been done for this system is that this protoplanetary disk has both dust and gas, and ALMA has measured the composition of the gas of this disk and found that the gas C to O ratio is greater than 1, so that the gas C to O ratio is carbon rich, whereas much more carbon rich than the atmosphere of the protoplanet itself. So the protoplanet is not as carbon rich as the gas around it. One probably obvious thing that could explain this is that the planet is also accreting solids, and those solids are also are probably rich in oxygen, and that is decreasing the C to O ratio of the planet relative to the gas that surrounds it.
So Brad's asking over Zoom, are these real atmosphere models or just really lineless? I think he's talking about
These are, yes, that's a good question. So in the red here, these are real atmosphere models, not just lineless. So we've put them through radio transfer codes. So KPIC has detected over 30 companions. These are both exoplanets and brown dwarfs. They span the whole range from 2 Jupiter masses all the way up to 80 Jupiter masses to basically the hydrogen burning limit. So here you can see this is a cross correlation function. So every peak represents a detection from one of our data sets. And what we can do is from all these data sets, measure the spin of all of these objects. So there's 2 ways in the literature to measure currently that we can use to measure the spins of directly imaged planets. One is if we have very precise photometry, and as the planet rotates, different amounts of cloud coverage changes. The cloud coverage changes as the planet rotates, and if we have precise enough photometry, we can measure that change in cloud cover over time to basically infer rotation periods through the light curve. The other way, like I mentioned, is that as the planet rotates, its absorption lines get broadened, and that measurement of broadening allows us to infer the rotation speeds of these planets. In the past, we have in the literature, people have found that generally planetary mass objects, those objects between 10 and 30 Jupiter masses, spin at about 10% of the breakup speed. So they're spinning not exactly near breakup. There's some mechanism to regulate their angular momentum so that they are spinning only at a fraction of their total breakup speed right now. In 2022, when normalizing this sample for age, we found maybe a tentative trend in mass that maybe as you get to lower mass objects below 10 Jupiter masses, there might be evidence for higher spin up. But these 2 points are Jupiter and Saturn, and they probably drive the whole fit that you can see here. So this is a very tentative thing so far. So we wanted to collect more data points. What we wanted to do is basically for every object, compute the rotation speed relative to breakup, and also to kind of baseline everything. We expect, planets after they have formed, when there's no gas around them anymore, they're just isolated objects sitting in free space. And they're going to contract over time as they cool, but their angular momentum should be conserved. There's no equivalent of stellar winds for planets. So as they contract, they should spin up. So because we observe planets at a bunch of different ages, some are spinning faster than others merely because they are at this different age of the system. So we want to normalize for that and evolve everything back to 10 million years, about right when the protoplanetary disk has dispersed. So how we do this is we measure the V sin I for all these systems. That's what we get when we detect these planets. The V sin I, to get the rotation period, we have to divide by sin I. So we can either assume that these planets have completely uniform obliquities, that they're randomly oriented in space, or we can assume that these planets have zero obliquity, that their spin axis is aligned with their orbital inclination, which we have a pretty good constraint of. We can also compute the breakup velocity. It's just square root of mass over radius. We have either dynamical masses for some of these systems, or we can use model-derived masses, which we think are pretty good. And we have also model derived models of its radius. And then for both, because the radius contracts over time, we have to correct for that factor and basically change the radius back to when it was puffier, back at 10 million years. And we also have to spin down the object, basically puff it up and cause it to spin down due to conservation of angular momentum. Sorry, I mean isotropic. Yes. And when we do that, we find this relation that we find this trend that planets actually spin faster than brown dwarfs. So we categorize all of our objects as either planets, definitely, brown dwarfs, definitely, and then the purple things are kind of, we're not sure what to call them. But regardless of that, you can see that for objects about less than 10 Jupiter masses, if you plot this in mass space, or less than about 10 to the minus 2 in mass ratio space, that's the ratio between the planet mass and the host star mass. Either way, you can see there's an enhancement of the spin speeds of planets relative to their breakup velocity for these lower mass objects that are much different than the brown dwarfs, which all seem to have a very consistent spin speed of nearly 10% of breakup. So below 10 Jupiter masses, it seems like there's evidence that these planets actually spin faster, and it's pointing to us the fact that there's some difference in angular momentum evolution at the early stages when the planet still has its circumplanetary disk to dump angular momentum onto. So I'm very welcome to theories for how this could happen. There doesn't seem to be a lot of theories in the literature, so if you have ideas, please let me know. I'm happy to chat. So we use the age of the star to calibrate for the age. So we've normalized everything to 10 million years old. So things that are maybe 150 million years old, we backtracked and basically unevolved these systems.
Except for Omaha, which is, I think, still controversial. What are the oldest planet mass objects that somebody has recognized?
So thanks. This is not part of my talk, but thanks to James JWST and its immaculate sensitivity in the mid-infrared at about 10 to 15 microns, we've imaged Jupiter mass planets at several giga-years old now. There's been a couple mature main Jupiters around like main sequence stars that have been imaged with JWST.
For this is the self-luminous Jupiter.
I believe they are self-luminous Jupiters. Yeah, they're not reflected light. Yes.
How do you read the radius?
How do we? So you just have to believe me that if we know the age and the mass of the planet, we can guess the radius from how we believe planets evolve and electron degeneracy pressure and things like that.
But there's like things asking to resume why you aren't just plotting angular momentum.
The angular momentum of the planet itself.
I guess the idea is that angular momentum is conserved, so you wouldn't have to do this backtracking. But
that's a good question. That's a good way of thinking about it. We just never thought about it that way, I think. But we could definitely do that instead. Yes, pretty. How do we estimate the age of a planet? That's hard sometimes. There's different ways to estimate ages. We use a compilation from the literature. The best ages are ages from kinematic membership. So if a star is part of a moving group or stellar association or cluster, we use those ages. Those are probably the most precise ages. Otherwise, there's a bunch of various bespoke ways to date ages of individual stars, and we just kind of used what's been adopted in the literature for each of these various sources.
The age of the star goes to the age of.
We assume that there's no delta between, planet formation we think happens on a few million year time scale. So if a star is 50 million years old, the planet is probably 50 million years old, or maybe it's 48 million years old, but it probably doesn't matter for the purposes of this study. Okay, I just guess I'll finish with one thing, which is in the ELT era, we're also talking about trying to image terrestrial planets with the extremely large telescopes. This is a plot from the National Academies of Science Exoplanet Strategy Report. It's again a little busy, but again, the y-axis is the planet to star flux ratio. The x-axis is distance from the star. You can see up here, again, this is where all of our current instruments are sensitive to. The green dots are simulated planets around simulated Earth-like planets in the habitable zones of nearby stars. We don't know if any of them exist. We're just pretending if they do, this is how bright they would be relative to their host star and how far they would be. And this shaded area here, between these two dashed lines, this is the sensitivity estimates of the ELTs. You can see that it's there's several orders of magnitude of uncertainty. And one of the reasons for that is that we don't know how good of an instrument we can build for the ELTs. All the ELTs are trying to image Earth-like planets using this technique that was similar to what we're doing in KPIC. Is first, you have an adaptive optics system to spatially resolve the planet from the star, but there's still the glare of the star that's hiding the planet. That the glare of the star here in blue is still many orders of magnitude brighter than the planet. And the idea is to use similar things like what we're doing in KPIC, using high-resolution spectroscopy to spectrally disentangle the light of the star, the residual light of the star, from the light of the planet to give us an extra boost in sensitivity by a factor of 10 to the 3, 10 to the 4, in order to image terrestrial planets around other, mostly M-dwarf stars with the ELTs. We don't know if this is possible, but this is one of the goals of KPIC, was to see, are there systematic, this is just a kind of a toy model, right? We're assuming there's no systematics, we're assuming perfect photon noise. This is how far we can go. The question is, are there systematic limits that prevent us from getting there? With KPIC, we may kind of make our first attempt to try to figure out if there are systematic limits. So far the answer is we don't think so. We're looking good so far. So this is our KPIC sensitivity curve. So again, on the y-axis is planet to star flux ratio. It's a lot less extreme. There's no 10 to the minus 8s or 10 to the minus 9s. We're talking 10 to the minus 2, 10 to the minus 5 here. What you see here in this black dashed line, this is how bright the glare of the star is. This is how much residual light of the star leaks into our spectrograph. And what you can see here in blue, this is the sensitivity curve of KPIC. We're basically able to filter out about 100 times the light of the star in order to detect faint exoplanets. And we're actually within a factor of 2 of the photon noise limit. This dashed cyan line is the photon noise limit. So we're actually we're near the photon noise limit right now with KPIC. This is after we identified and fixed a bunch of some unanticipated systematics, but we figured out what those are and know for the future to never build high contrast instruments with those things. You can ask me about those later if you're interested. But yeah, that's small angular separations from the star. We're within a factor of 2 of the photon noise limit, and we're hoping, like I said before, we want to push to be able to get a gain from our high resolution spectrograph about 10 to the 3 to 10 to the 4 times, so that we can show that we could, if deployed on the ELTs, we could get that same sensitivity to reach exo-Earth sensitivities. Hopefully the upcoming high-spec instrument, which is being partially built here at UCLA, will give us, will help push this technique to see if we can actually achieve those kind of extreme contrasts with high contrast imaging plus high resolution spectroscopy. I guess in the interest of time, I'll stop here. But if you're interested about optical interferometry, I'm also happy to chat anytime about optical interferometry.
Okay, questions for Jason? Bjorn?
Yeah.
Yeah.
So on your very last slide, you showed that factor of 100 gain by
Yeah.
using the high resolution
Yeah.
spectroscopic information.
Yeah.
And you're close to the photon estimate.
Yes.
But if you had more integration time,
Yes.
with this, could you go lower with this?
Yes, we could, but it goes to square root of t, right? And we're already talking about 4 hours of integration time here. So if you want another factor of 2, you need to go 4 times longer. So that's 16 hours. So yes, we can do it, but it's very inefficient. So probably waiting for high spec is probably a better way to push for it. Yeah.
In front.
You're talking about the fundamental image or fundamental noise limit?
Yeah.
For the computational imaging?
Yeah.
What is that defined by?
Oh, yes. It's defined by two things. One is kind of detector noise. So like we have this like thermal electrons and things like that. We can't avoid those things. These random processes, basically inherent random processes. The other one is photon counting statistics. The arrival time of photons is inherently random. So if you have a lot of photons, how many photons you expect in a given time is an inherently random process. So that inherently produces noise in your images. So those are fundamental limits that we can't overcome no matter how hard we try.
I'm really interested in this boundary
Mhm.
top. So you showed us the spin, for example, and other
Yeah.
things, and I want to ask about something, I want to follow up on something that you and I talked about,
Yeah.
the eccentricity.
Yeah.
Did you look at eccentricities as a function of distance from, and also the mass, the primary mass that there is? Because if I have triple brown dwarfs, maybe they'll behave, or few multi brown dwarf system, they'll may behave differently than a star with brown dwarfs around it. So
Yes, we have not. It's hard to look in too many parameters because we have not that many directly imaged systems. So when you try to divide up your bins and then into too many axes, we run into Poisson statistics. Basically, there's not enough numbers. So it would be interesting to look into some of those things, in particular things like how do the eccentricities of planets in single systems versus planets in multi-planet systems compare. I don't have the answers for you, but I agree that those would be interesting to look at.
I know that you mentioned the software you're providing for the Roman vertigo, that you're interested in software development as a whole. I was wondering specifically if you're running through an Astro for this summer, 2026, or if you have any details about that. I'm an undergrad.
Okay, Code Astro is a software engineering workshop we run. We are still figuring. We're still figuring out whether we're going to do it for 2026. Funding pending. If we get funding, we will do it. If we don't have funding, maybe stay tuned. Basically, I can't say anything right now. Yeah.
I think I saw a hand in the back.
Yeah, so if it's a variable star,
Mhm.
and you're trying to the image of planet around the star, how does the fact that it's a variable star affect things in that? Is it like an advantage? Can it be helpful in some form, or do you think it might?
That's a good question. I can't say we have been we have the sufficient amount of photometric precision or sensitivity to use that fact right now. Basically, a variable star would just move the speckle levels up and down, and I don't know if that will help us in much of a way right now, I would say.
Evan?
Hey, thank you for the amazing talk. I'm curious about the planet that Natalie discovered, the circumbinary planet of the circumbinary system. What was missed the first time around, and then along with that, does this give any hope that we'll be able to find even more planets in the same manner? All in archives.
Yeah, I think it's a good question. So I guess I said miss, but not necessarily miss because we never finished finalizing parsing through all of our candidates. With the finite telescope we tried to prioritize the most promising candidates. And we indeed tried to follow up this object, but it was taken in really bad weather, so we could never confirm or refute it. And then the survey ran out of time. So what we were able to do this time is take advantage of the fact of archival data that other people also decided to look at this object, but didn't quite follow up this blob and piece all those pieces together to confirm that this planet was indeed real. So it was a combination of we didn't prioritize this object high enough, and a combination of we just ran out of telescope time, or the conditions weren't good enough when we tried to actually follow up this object.
I'll ask the last question.
Yeah.
What about Roman sets this limit of 10⁻⁸?
Yeah, it's a very surprising thing. It's the size of the secondary obscuration in the primary. So basically, if you have a telescope mirror, it's a circle, right? But oftentimes the light of the mirror bounces off the primary, hits the secondary mirror before it goes to the rest of the instruments. That secondary mirror casts a shadow on the primary mirror. That's the Roman secondary is very large to have, basically produces very fast survey telescope, probably for surveying large parts of the Earth for national reconnaissance purposes. It turns out by having a large secondary obscuration, you suppress the ability of an optical system to control intermediate spatial frequencies. Like, what does that mean? It basically increases the amount of glare at separations right around the star, not exactly doesn't aberrate the star itself, but at a few lambda over d around the star, it causes aberrations that are hard to control. And that exact area is where we want to do the dark hole digging to search for planets. So basically, that secondary obscuration makes it so hard to build a coronagraph and wavefront control to suppress the glare of the star that sets the limit for how faint that sun-star contrast limit, basically.
Great.
Yeah.
Well, yeah, thanks for answering all of our questions. So let's give Jason another round of applause.